Hello, everyone. I hope that you had a nice lunch break and that you recover from the control theory lecture. Now we are... It was a really nice lecture, so thanks, Ardallah, for that. So I will introduce the next speaker, Michal Koslowski.
Yep.
Okay, thanks. So he received his PhD in 2019 from the University of Bristol. He worked as a postdoctoral researcher at Harrows University in the Air Lab there, and he was also a research associate at Imperial College London, and now he's working on machine learning and computer vision in Kidsloop Ltd, still in the UK. And he will give us now a lecture on underwater vision and localization. So you saw control before, and now we look at the sensors and how to use them. So, Michal, the floor is yours.
Thank you very much. Hello, I'm Michal. Thank you for the introduction. Thank you for a warm welcome at Romaro. And I'm hoping that the lecture is going to take about an hour 30, an hour 40 minutes, and then we can have a practical session later on. Like it was said, this is going to be a bit more application-based as opposed to theory-based. So I'm hoping that for the afternoon, this is a good, nice session for everyone to kind of maybe not relax, but definitely gear down a bit. So yeah, shameless plug of myself. I don't think I have to add anything else. I think that was said just now. Kind of learning objectives. What I want to cover today. I want to initially kind of talk about sensor modalities for navigation. This is going to be a more general understanding of navigation. So I'm going to talk about anything that's being used, for example, in any kind of drone, UAV, and even human localization. And then I'm going to go more specifically into underwater kind of perception. So we're going to cover like sonar, we're going to cover vision. So this should take right about 40 minutes, maybe half an hour. And then I'm going to spend another hour, maybe an hour, 10 minutes on giving you a crash course on Bayesian filters and Kalman filters. I'm hoping that whatever equations I have put in there, I'm not going to scare you. And then finally, at the end of the session, I'd like to run a practical session, which I hope that you all received my email and have prepared accordingly. And if you haven't, then I'm sure we can figure something out as we go along. A very basic kind of, I want to start with a motivation around navigation. And this is an example from, one of my favorite examples actually from history. Back in the 16th century, maps, especially the Spanish maps, would describe California, as the peninsula of California, as an island. Now, we knew as explorers, they did know that California wasn't an island, it was part of the continental United States. However, there were a number of different books that described California as this El Dorado, as this Garden of Eden, where you know, everything is made of gold. And interestingly enough, it took them around 200 years in order to finally correct the maps and kind of attach, if you will, California back to the continental United States. So I always joke that it's an example of a very poor loop closure that took them about 200 years in order to finally close the loop and have the California finally attached to the. Thankfully, we now come up with the algorithms that that do it much quicker than 200 years. So in a very kind of initial stage, I think it's not unfair to say that the most foundational of sensors you can find, especially in any practical application, is going to be inertial sensors or inertial measurement units. They're usually kind of enclosed MEMS chipsets. They include, sometimes they come packaged along, accelerometers come packaged along with the gyroscope. Sometimes accelerometers themselves are kind of alone in the package, if you will. So this basic graph explains how the accelerometer and the gyroscope are kind of sensing. So the sensing domains, you can imagine that where accelerometer calculates or measures acceleration across all like 3 cardinal directions in our three-dimensional space, then that gyroscope is going to calculate the angular velocity around those axes. Right. This is obviously, if you have a perfect sensor, you would basically assume that due to the fact that you can calculate acceleration being the second derivative of position is going to, all you'd have to do is integrate it twice in order to get the position. If you have a perfect sensor, which one that doesn't exist, unfortunately, you would basically be able to predict where something is in space. However, the problem with inertia is that you would, as long as you start to integrate for longer time horizons, you'll find that as soon as you start encountering noise, like this big blob there, as soon as you start encountering noise, you will start compounding error. And whereas it is very useful for kind of shorter time horizons in terms of kind of state estimation and kind of spatial awareness, for longer time horizons, inertia on its own, of course, might not be the best option that you may have. Obviously, the more you pay for the sensor, the better the sensor will be. You can spend millions on the sensor, and it's going to be, the noise floor itself is going to be quite low. But yeah, not everybody has that much money, and the ones which go for about 30 cents, yeah, this is what they'll give you. A lot of navigation, obviously, nowadays is done with cameras and vision. This is something that I'm kind of mostly kind of involved in, if you will. They range from anything, from monocular cameras, from stereo cameras to LiDAR. There are a lot more than this, of course. Recently, actually, there's a lot of research going into event-based cameras, which is very exciting as well, especially from ETH. So I kind of think that this term camera and vision kind of encompasses all of this into one umbrella. So what you're seeing here is a very kind of basic epipolar geometry reconstruction, whereby if you, obviously, I'll talk more about stereo vision in a second, but basically illustrates that if you have two kind of points of reference, if you will, or scenes, or two images of the same kind of scene, but offset by a certain amount of distance, then you can basically, if you manage to match the features together, then you can reconstruct, at least in theory, you can reconstruct a stereo and depth and kind of give you more information from the reading. This is quite interesting as well. This is something that I've done myself. This was a data collection we did back in the day. It was right after my PhD finished. This is a passive LiDAR, which basically was standing in a side of a room. The room was about the same size as this, and the idea was that we would put the LiDAR, and then we would try to track a person inside of that room using just the passive LiDAR. So the LiDAR itself doesn't change position. So the idea here is that we can basically extract the background from the human. And the human itself is going to give you a three-dimensional silhouette, or three-dimensional bounding box, excuse me, of where the human is. Obviously, you can see that it does kind of oscillate. It is quite noisy, but there's one thing that you learn across this presentation is that I'm afraid everything is to do with noise, and you can't really get rid of it. So yeah, monocular vision, as the name suggests, very simple. They rely on singular lens and kind of output from a single source. They're good in terms of computation, and what I mean by that is that if you have an algorithm that relies on a monocular camera, then it's going to be a single image source. There's no disparity to compute because there's nothing there's no parity, so there's no disparity, if you will. However, it suffers from what's called a motion scale problem. And the problem is that that particular type of camera, or that particular approaches, they are unable to synthesize what's called scale of the scene. So if they see something in their own frame, then obviously this is relative as opposed to an absolute scale of what they're seeing. So they cannot compute how far, for example, something is away unless you have something else to tell it how to do this. And thankfully we do. So stereo cameras kind of solve this problem, and they do this by computing the relative disparity. It's called epipolar geometry. And the idea is that if you have two cameras, much like your eyes, if you have two cameras, then you're going to be able to find the same features in two frames, and then try to compute the disparity between those features, and from then on you'll be able to compute the depth. So the depth obviously gives you an additional dimension to your readings, and this can be used, I think, most popularly, or kind of initially, if you will. This was used mostly for kind of obstacle detection. So if you were going forward and you'd be able to see something approaching you in terms of depth, then obviously you would want to avoid that. There are ways, and there are problems with depth. Obviously, there's, as with any algorithm, for example, the OpenCV implementation uses something called stereo block matching. And obviously, with the stereo block matching, you would need to define some form of a window in order to match the frames or to match the features together. If you have an obstacle small enough in frame, then obviously you're going to miss it. This is something that we've experienced back in the day, but I'll show you a bit later on. Yeah, so it requires very good features to compute that disparity. Obviously, you need to see the same thing in two cameras at the same time, and it suffers in poor lighting conditions. So, as with any vision problem, occlusion and poor lighting is going to be the biggest problem. LiDAR, quite effective in terms of sensing. Uses time of flight in order to scan the environment. The solid-state LiDARs, there are normal kind of LiDARs scanning the kind of 360 degrees of environment as you walk around. They're typically used in kind of autonomous driving tasks. Obviously, there are many different flavors, many different approaches that people use to use LiDAR. But I've found them used more kind of in industrial scale. Obviously, you see them in autonomous driving tasks, mainly due to how heavy they are and how much power they still require. So if you were thinking about having a UAV that is flying through, that needs to fly, for example, for 10 minutes, obviously the motors that are keeping the UAV in the air are going to be the biggest, kind of the most power-hungry kind of plant in the system. And what's going to happen is that you're going to drain a lot more power. And obviously, if you have a heavier sensor and also the fact that you have to still power it and have the laser beam at a really crazy speeds, then it also kind of brings the battery life down quite a bit. So this is what I found that obviously if you have autonomous car, you can fit as much battery as you'd like. So it can be used like in a hybrid system with a monocular camera. So this is actually one of the ways that we can synthesize scale, and we can synthesize understanding of depth in the monocular system. So plenty of other approaches to navigation. Something that I've done during my PhD actually was using RF, or radio frequency. We used to use a Bluetooth low energy protocol from different routers in a kind of prescribed two-dimensional space in order to kind of track someone through a house. Obviously, if you're walking around, you can think of a radio frequency ranging as kind of a trilateration or n-lateration of signals between the source and the transmitter and then the receiver. Sorry. And the idea is that you obviously can trilaterate different places in the house, and then from that you can learn what signal sources there are in a specific kind of area, or however low you want to tessellate your state space, and then from that you can kind of localize someone inside the house. So I was actually hoping, if you look at this picture, and I wonder if someone can tell me something about the noise of this. So you can see that there is so there are sample numbers, so this is basically the sample rate, and then you have the RSSI, which is just basically the received signal strength indicator. So this is just basically power coming from a specific access point back to the receiver. And what's interesting, maybe someone can tell me, maybe not, is that the noise is very kind of normally distributed, right? So you can see that the noise and the actual kind of dispersion of the points around with time, you can see that this is something that that's pretty standard and pretty equal across time, and this is something that we also exploit when using kind of Kalman filters in order to calculate where we are, and this is exactly what we've done in the past as well. Right. Also, I've read papers talking about using magnetometry in order to localize a person or like a UAV in a kind of residential building, and the idea was that the actual kind of supports of a building, or like the steel beams around the building, would bend the magnetic field, like the passive magnetic field of the Earth in a certain way. You can learn this patterns, and then you can kind of regress that onto a state space, kind of localization state space. It's quirky to say the least. I don't think I've seen anything kind of more pretty effective using it, but it's a very good idea, and I quite like it. Also, acoustics. Are we going to talk more about this in? We're going to talk more about this in the next section, or obviously when we come to LiDAR. Sonar. Okay, so this is a drone. This is a drone that we made back in the day. When I was at the Air Lab in Aarhus, this drone was obviously a quadcopter. It had 4 engines, and it had a single stereo camera in the front. You can ignore this camera, don't worry about it, it doesn't exist for now. But what I want to say is there is a reason why sensors cannot really work or cannot really work effectively on their own, right? They need some form of kind of support, or perhaps fusion with other sensors in order to kind of function to their best ability. And this is something that we found. This is something that we found whilst researching SLAM applications on our drone. So the idea is that we had a specific brief. The brief was that the drone itself has to be flyable. It needs to navigate itself in an environment and don't crash into anything. Obviously, that was easy enough to say. It was harder to implement. And the idea here was that we were using a stereo camera in order to have that information from the depth. So a number of different SLAM algorithms use kind of stereo implementations of this, and you can track the features through the space. The problem here, however, was that because this camera uses what's called a rolling shutter. So you can imagine that the shutter itself, the refresh rate of the image, kind of rolls around in kind of the sequential lines across the screen. And when that was happening, the engines were giving quite a high frequency vibrations. I'll show you here. This is us carrying the drone. Hello.
Are you sure your microphone is on? Just worried about
Yeah.
recording. Okay, it's on. Okay.
Yeah. So this is us carrying the drone in our hands. This is kind of a rest period, and then you have the engines kind of working and the drone actually flying. And we found that because of this kind of rolling shutter effect, what ended up happening quite a lot is that whatever features we were trying to work out in one screen or one camera would not be matched correctly to the other camera, and we would lose the track from the drone really, really quickly. And so what did we do? I should also mention, okay, this is an accelerometer reading from the drone. So this is an accelerometer reading from an autopilot implementation called Pixhawk, and this was basically showing us the vibration on the kind of what's called the base link of the robot. So this is basically what the robot itself was experiencing. Now, because the base link was quite close to the camera, we figured out that the camera would require some dampening, and so the engineering that we did was put rubber dampers in the camera, and it worked out very well. And you can see now that the noise kind of reduced, and we could basically now work the SLAM quite effectively. So thankfully that was solved. Now I'm hoping that as we go along in the presentation, I can. I'm going to home in on the underwater and kind of algorithms, but the general kind of introduction was quite nice. So anyway, talking about sensors, as you all know, so if obviously collective name for sensors using sound waves in an information medium, as an information medium. So they're very well suited for long range kind of information carrying underwater, and the propagating sounds work on a kind of principle of compressions and refractions in a medium, right? So I'm sure if you work with sonar, you know exactly what I'm talking about. But that's just like I guess it's just for me, so I know what I talk about. So they're broadly classified as kind of passive, or active. Passive signals can be generated through any kind of natural occurrence or consequence. Things like sea creatures, ship motors, sea itself, also quite noisy. Sea creatures, you know, like whales calling out to each other. And active signals through deliberate sonar pings, right? So if you've ever seen any of the Hollywood films with Sean Connery or Harrison Ford, I recommend you do. They always say, "Give me a ping," and then it pings around. And yeah. So a ping is generated in the source, kind of in the form of a spherical wave. The wave then bounces off some reflector and also comes back as a spherical wave at a kind of a reduced rate when it comes to energy. The relative range in the signal of the signal would depend on the distance traveled, dissipative properties of the water, but can be broadly generalized with this equation, which is range equals speed times time over 2. So this is just like a basic understanding of the sonar. So some of the uses for sonar, obviously I've mentioned defense, bathymetric studies for underwater detection. So this is something that it's quite broadly used, kind of mapping the surface or the floor, the sea floor of the sea, and then we'd be able to kind of know exactly what's underneath the water. Pipeline inspection, I know quite a few of you work on that. Offshore turbine installations, search and rescue, many more. Basically, it's the best thing we know how to do in the water, at least for now, and it's being used as such for anything that we could say. There's also a kind of principle of acoustic positioning. So again, in principle, the positioning is done with an acoustic transducer in a vessel and a corresponding transponder in an underwater robot. If kind of a model parameters, which we should know, like the space transformations, are known, then we can estimate the position through kind of travel time and phase shift. It takes, unfortunately, the problem is obviously the finding out the space transformations and it can be quite a laborious way. So this is more of a model-based approach you can think of, and there are different kind of a number of different methods that were proposed, and ultimately all rely on kind of the model parameters and to estimate the position of an underwater robot. In case you're wondering what papers there are, the presentation I'm sure will be available. I keep the references down on the at the bottom of the slides, but you can also find them obviously at the end of the presentation. So if you're interested more. So quite a few approaches also include kind of optics and vision. And optics and vision obviously very challenging underwater because of, well, one reason or another, but mostly due to kind of light condition visibility issues and as you can appreciate, the amount of like the difference or the relative difference of how kind of visibility underwater can vary in different kind of bodies of water, right? So you can have very clear images. Obviously, you can have very kind of muddy images, something that is pretty much unusable for navigation, especially. So if we're talking navigation here, we're talking mostly SLAM, for example, right? But there do exist methods which concentrate on kind of improving the image quality, and there are two ways to do this, and one is model-based, and one is data-driven. So, you know, the ultimate showdown in academia, I find. Model-based, obviously, you can vary your color or vary the contrast of the image in order to improve the quality. Some approaches actually employ, it's like they kind of go as far as try to employ a model which defines image degradation, so-called Jaffe-Montgomery equation. It's a very laborious process. The problem, obviously, is that you need to actually sit down and work out what governs the poor quality of the image itself, and then try to remove it. So again, as I said, very laborious. Something that I'm more interested in, which is just data-driven, so throw data at a deep net and it'll work. I'm sure most of you have, or many of you have used WhatAgain. Very interesting how they kind of pipelined it together. They try to perform kind of color correction of monocular RGBD images. But RGBD, again, another vision. It's another vision example, which is basically an RGB camera with the depth kind of sensor, usually with like an IR, for example, that ranges, gives you a depth information, so you can have this, the computation advantages of a monocular sensor, and also this the knowledge or the notion of a depth, the notion of kind of an extra dimension, if you will. So you can basically what they claim to do, or what they try to do, is that they can basically feed the network with images, and they're kind of paired together. There's a parity between image that is kind of noisy and obviously not noisy. If you feed enough of the same image that is kind of noisy and not noisy, you eventually learn the underlying kind of function of the noise. And then when you're seeing and when you're fed an image that you haven't seen, you obviously can try and filter it out. So I think this is how WhatAgain does what it does. So I did have a look at object tracking. This is something that I'm interested more in a context of kind of UAVs. I'll show you in a minute. But there has been some research done in underwater object tracking. Again, deep learning as much as anything, and YOLO and RCNN are the two kind of state-of-the-art for now that we know that are being used quite extensively, not just for underwater, but for many other approaches as well. So the main difference between YOLO and RCNN, that you can think YOLO. I'm going to give a human as an example. YOLO will give you a bounding box of a human, right? So if you see a human in a frame, it gives you a square bounding box. Whereas RCNN is going to be kind of more detailed, and it's going to give you kind of pixel-wise map of a human in a scene. Both have advantages, both have disadvantages. What you use is ultimately up to you. But they will too obviously suffer from poor performance if you don't pre-process the underwater image in some way. And so I'm also hoping that the practical session that I kind of prepared and the dataset, underwater dataset, sorry, it's going to show you quite clearly how underwater SLAM is very, very challenging, mainly because of it's many different. I'm not going to spoil it for now. So many other kind of sensing and perception for underwater. Again, magnetic. Maybe I'm just really interested in magnetic sensing, but I did find something using passive and active kind of magnetic field positioning. So it's either that the sensors themselves are sensing the induced magnetic field from the Earth, or like the passive Earth's magnetic field, and trying to regress that into a model. Or you have like an active magnetic field positioning, which is obviously something from a source that we generate ourselves, and this is something that we can that we can account for, sense, and ultimately localize something underneath the water. So it works on a similar principle to acoustic positioning. Obviously, you would need some form of understanding of the source. You would need some form of understanding of the receiver. But it doesn't. There's no need for this expensive infrastructure, especially when it comes to this passive field from the Earth, and it's also not as much affected by the water, especially in terms of like longer sensor ranges. It's not as affected by water, but it can be. Any minerals or metals in the water are going to warp the magnetic field, accordingly. Cool. So this was the first part of the session. I'm hoping that the next part, actually, I'm making good time, I think. So the next part of the session, I'm going to talk more about theory. So I'm going to talk more about kind of Bayesian filters and Kalman filters. I found this resource that I thought was like absolutely like excellent when it comes to this. So if you're interested more into like doing Kalman and Bayesian filters in Python, I recommend you check it out because yeah, it's excellent. Just let me have a drink and then I can go now. Cool. So let's do some equations. We can, in order to define a Bayesian filter, you can define. We can define using notations from robotics, kind of a classical robotics, if you will. You can define a set of discrete observations using the letter Z. Observation in this context can be anything from a LiDAR kind of beam model to a radio frequency, signal strength, anything that gives you some observation of the current state using the outside world is kind of viable here. Set of discrete actions. Obviously, there's an action, especially in terms of robotics, there's an action that a robot can take. The actions are defined with the letter U. The actions obviously can be anything. For example, a robot moving the manipulator in order to perform a function. And the idea here with the actions is mainly what we want to define is kind of a change of state. So if there is a kind of observation action model, we want to know if an action can change the state that we're currently kind of occupying. And obviously you do have the states defined with the letter X, and I'm hoping that because I'm using the states for the letter X, I'm not kind of tiptoeing on out of the previous lecture. You can think of this as more a kind of less abstract than the previous lecture. You can think of a state as, for example, a two-dimensional coordinate in space, right? So this x1 could be defined as a vector of y and x, or x and y, sorry. So this is something that you can put kind of you can put context towards. And additionally, a Bayes filter assumes that we are given a sensor model. So the probability, or the table, the conditional probability table of a specific observation given a state. So how likely is that particular observation to be occurring in that particular state? And also action model, which defines the kind of the change of state given an action taken. So if you're currently in a state X, we can say the probability of us, the X dash, the probability of us kind of changing into state X is given as given by the action we take and the previous state in which we have found ourselves in. And ultimately, what we'd like to do is we'd like to find a kind of posterior belief of any given state, given a set of observations and actions. There's this notion of kind of sequence of given an action, you can also measure what that action has kind of inferred in terms of your state space, the kind of a robotic state space. So this is something that we are going to be using. I should also mention that there's quite a bit of derivation here, which I didn't include in my slides, and I definitely put like a little note that you should use time at home and do the homework and do it. I'm kidding. But I'm hoping that it's still going to be clear from the context what we're trying to do in this. So you can recall Bayes' theorem, very basic. If you've done kind of statistics of probability, I don't know, even like high school level, I guess, then you should be kind of familiar with this, which basically means that there's the probability of a variable given another variable, kind of a posterior probability of a variable given another variable, is dependent on this likelihood and the prior probability of, in our case, the prior probability of a state given an evidence factor or normalization factor in a kind of a Bayes filter nomenclature, a normalization factor which kind of normalizes the probability. And this is exactly what I mentioned. It definitely doesn't come from empty space. Like there is a derivation again to this. However, I'm just going to use the kind of the derived formula, and I'm going to say that this is basically what we'd like to use. Yeah, with the eta element being the normalization factor. So there's a good way to predict this, or like there's a good way to utilize this. If you kind of separate this into two distinct elements, and obviously if you've done Bayesian filtering or Kalman filtering before, you'll know the notions of update and prediction. But for those who don't know, you can basically separate this equation into kind of their own separate equations, and from that you're able to more computationally, more efficiently, perform this prediction and update kind of one onto the other. So in the update step, you will basically try to predict what's called a prior. The prior is going to be defined by this, the model of your environment. So it's going to be defined by a measurement model given a state. So this is, if you've ever done any data-driven methods, this would be basically you walking or you collecting data which correspond to a specific state. And from that data, you'll be able to say this measurement is this likely in this particular state, and that's how I know what the probability of it is, including the belief from the previous kind of iteration of the estimate. Obviously, since we don't have the previous estimate, we can use the prior from the previous, the prior which we can define ourselves. Kind of in the first instance, obviously this will be recalculated as we go along, and as more evidence and more observations are being given to us. And the prediction step is mostly concerned with how likely a specific action is to change the state that we are currently in, right? So if an action can be defined, or if an action can has an ability of changing our state, then this is going to kind of calculate the belief that we are we are likely to leave, or we are likely to stay in the same probability or the same state as we have been in the previous time step, or not, basically. So I know this is quite abstract, and I'm going to put a very silly example on now, basically trying to figure out, and you'll see that this is a actually very basic process. So this is actually based on a cat, my sister's cat, Stefan. The cat itself is he has two states, and somehow, yeah, we can think of this as the cat can be either inside or outside. So imagine that we have an access to this GPS sensor, and the GPS sensor, noisy as it is, we can attach it to the collar of the cat, and the cat can say, oh, yeah, the sensor is going to say whether the cat is in or out. We also have access, I don't know, through magic deep learning somehow, to the needs of the cat. So the cat knows, so we know what the cat is intending to do. So we know that the cat would like to be lazy or would like to go on patrol and outside, right? So we can immediately define some very basic priors in that since we only have a binary state space, the cat can either be inside or outside. We can just define it as being as equally inside as equally outside. Now this isn't a Schrödinger equation or anything. It's a pure coincidence. But the idea is that we'd like to have a prior that that defines the initial kind of step zero, if you will, for our method. So it can be as likely inside or outside. So we can define some sensor models. So this is exactly what I mentioned. So you would go along the cat and kind of calculate some form of data set of whenever the cat is in or whenever the cat is out. How often is the corresponding measurement from the GPS actually telling you that it's in or out? There's a reason, obviously, since they're not equal, and there's a reason for this. Obviously, the more no sensor is perfect, and since it's not perfect, then I hope that it's it's going to be quite clear to everyone that yeah, we can still get a GPS, for example, a cat GPS signal as sitting outside, even though the cat is inside, and so forth, so forth. So this is some sensor models that we can define. With the data set. We can also define some action models. Obviously, everything is done on the kind of this notion of kind of binary state space, action spaces. So the idea is that the cat can only ever go on patrol or be lazy. And so if the cat just wants to be lazy, the state space that it's currently occupying is not going to change in any way, right? So there's not going to be a state of transition if the cat decides to sit at home. So if a cat is outside and wants to be lazy, he will stay outside, and that's the only thing that is not likely is that we can't really predict what cats want, but we can just assume that it's one. And then if the cat is inside and wants to be lazy, the cat is going to be inside. So this particular action model is not going to kind of change the states or change the state spaces that we're currently in. However, the states for going on patrol are going to change it. If the cat is, for example, outside and he wants to go on patrol, he's going to obviously go outside. So he's going to stay. He's going to. This should be actually. Sorry, excuse me. This should be x t minus 1. So this is the state prior. Yeah, so on and so forth. So if the cat, for example, is outside and he wants to go inside, given that, no, if the cat is inside and he wants to go on patrol, then what's the probability of the cat being outside? And obviously that's going to be higher. And so this is just a very basic example. Obviously, if you have an integral in a more kind of numerical way, numerically you can just define it as a sum. So you'll find that this should actually just be a bunch of multiplication and addition, which basically specifies that if you go back here, you can see that the probability, obviously this is the action space, this is the belief, and this belief is going to be the belief at x equals, or t equals 0, which means that this is the belief of a kind of a prior belief. So you can recall that the prior belief we had was half and half. So this isn't anything that we know kind of for sure. And then the action space that we defined before, which is the cat in, cat out, like kind of the numbers are given here. And so here now the idea is that we would like to sum the fact, we would like to sum some symbols, or we would like to put some numbers in it. And so we'd like to sum over the symbols that define the cat being either inside or the cat being outside. And so if we define this as how likely is a cat going to be outside or inside, given that he's going to go on patrol, you can just kind of multiply the probability of a cat being inside, which is a half, and the probability that he wants to go on patrol and the cat is in, which itself is 0.7 and 1. So the probability of a cat being outside and the probability of a cat being inside is 0.15 and 0.85, and this basically specifies this is your update step. The prediction step, which basically specifies the prior for the next step that we're going to do. But the idea is easy. So you can now see the update step, which in itself uses the actual measurement model and the probability of a measurement given a particular state. So this is going to be the GPS that we defined in the past, and the belief that we have here. The belief is the belief that we've just calculated in this step here. So these two beliefs give us a prior given our model, and then from that prior we can calculate the belief of the cat being either in or the cat being out. And so again, you can just literally fit the numbers in, and this is as simple. So this is simple when it comes to kind of a binary state spaces. Obviously, if you have a bigger state space or even continuous state space, then the problem becomes kind of infinitely more difficult. But this is as simple as I could have made it for this exercise. And I don't know what I did. Yeah. So base filters are kind of a foundation of a variety of different approaches. among them, obviously, Kalman filters, particle filters, hidden Markov models. So they kind of govern. They govern the whole kind of family of these state estimation or state estimation approaches that we have currently. Hidden Markov models particularly interesting because it doesn't actually include any action space, so we don't really know what the action might be. Instead, it has access to what's called a transitional kernel, so a transition matrix. So if you've defined your elements, or if you've defined the states, you can basically specify how likely a transition is from state to state given a transition, like kind of a transition probability matrix. Cool. So I'm going to go on to Kalman filters now. Are there any questions about Bayes filters? Or the stupid example.
So this normalization constant, do we have to maintain it, or can I just ignore it?
It's going to recalculate itself at each step. So this is something, obviously this is...
We just need the relative values of
Yep,
different
that's right. Yeah.
I would just forget the data.
You could, yeah. But if you, obviously it bounds it nicely between 0 and 1 if you want to do that, but yeah. No? Cool. So very basically, in order to start with Kalman filters, I think it's important to talk about Gaussian distributions and kind of giving you a primer on Gaussian distributions. Probability density function, kind of a unimodal probability density function parameterized with two parameters, mean and standard deviation. And the general form of the distribution can be given as this equation. I've included it as a reference, but I'm not going to really use it for the rest of the presentation, but it's just nice to see that there is a form that makes it look like this. This is from Wikipedia, and I just wanted for you to know, who can tell me, without me saying anything from now on, I just want to know how much you know, how much you guys know. Given these kind of parameters and given these distributions, which distribution would you be most confident in, given that you from your high school probability, and least confident in? Who can tell me? This is by the way the absolute crux of Kalman filtering. So if you can imagine how to calculate a mean and how to calculate standard deviation, obviously the bigger the spread of the observations that you're trying to calculate is going to give you a bigger spread of the distribution, thereby a bigger standard deviation that you have. So if you were to see which one is the most likely or the most we are the most certain of, then I would say that the blue one obviously is because of the low uncertainty that we have as encompassed by the standard deviation. And conversely, the most uncertain, I would say, is the yellow one because of the relative size of it, right? So I hope that's understood, because that's going to be the, yeah, okay. Cool. So it has a number of kind of nifty properties to go along with it, and as it turns out, Gaussian distributions can be summed together to create another Gaussian distribution. So if you have two means, you have two standard deviations, you produce it will produce a mean and a standard deviation. Now, again, this is there is a derivation of this. It's actually based on convolution. So I invite you to go to Wikipedia to work it out. But ultimately, this is it. If you have two distributions and they are IID, you can do that. Also, you can multiply two Gaussians together. Same story. Derivation is for homework. But the idea is quite important. So I want to show you mainly why, because Kalman is actually simple to understand in theory, but quite difficult to understand no, the other way. It's quite difficult to understand in practice, but in theory, it's actually quite simple, because it's just this kind of loop that predicts and updates given observations from a sensor, for example. Yeah. So it's going to, a Kalman filter works on the same principle as a Bayes filter, obviously, since it's based on it. You update the model using the current observations, and you predict the state. And you kind of do this recursively, well, not recursively, but you keep doing this until you converge onto your appropriate readings, if you will. So the only difference is that it's doing so using a Gaussian distribution and kind of strictly Gaussian. So this is one of the main assumptions of Kalman filters, is that it can only these are the ones we know of. It can use strictly Gaussians, and this is mainly because of these properties. So we can basically add and multiply Gaussians together, and this is what makes the whole Kalman filter can work. Also, I should mention that the filter that I'm going to explain to you here is just the pure Kalman. It's not like extended Kalman filter. So this works only on kind of linear systems, right? So if you have I'll show you in a second, but yeah, linear systems only. So prediction in kind of one-dimensional case of Gaussian distributions is as simple as adding the prediction in one-dimensional case of Kalman filter is as simple as an addition of two Gaussian distributions. And this is mainly because if you can consider the fact that we have some certain state in our localization kind of context, we can obviously say this is a location on a unimodal, like kind of one-dimensional line. So if you imagine you only have one-dimensional world and you can only move in one direction, then we can define a state just by a position from, or like relative position from the origin. And then from then on, you can see how that position changes given some form of a process. So process model, this variable here actually defines how a process, or like how the state is going to change given some model. So in terms of positioning, in terms of kind of localization, the most likely thing you're going to encounter is the use of obviously velocities and accelerations. So what I'm going to define the problem in terms of velocities and accelerations, but obviously if you were to using Kalman filters, which they are being used, for example, in financial sector, obviously they don't use velocities because pointless. So in terms of our kind of in our understanding of the Kalman filter, the fx is a process model. The process model itself can be defined as a constant motion, kind of a Newtonian constant motion, which obviously is defined with velocity and rate of like in a step change of time. So is it clear from till now, or am I just talking too much? Cool. Yep, so we can continue. And obviously, since we can define the process model itself as some form of an uncertainty, then you can also define it in terms of a Gaussian distribution, right? So if you know what your current position is, and you know what the kind of measurement is that you took with a sensor, just imagine like an abstract sensor, then you can define the prior probability using both the means and the standard deviations of both of those. So if we, for example, in this context, you can have a position, for example, position 2 meters from the origin, and you can have a standard deviation of that position. Say we don't know where we are within 50 meters or something silly, right? And if we have a measurement of a position, so for example, if we have a sensor that measures where something is on that particular one-dimensional line, you can also define it as a mean with the uncertainty of the sensor encompassed into this standard deviation below. And so in this case, this is quite powerful because if you think about this, we have a position, the current state that we are. We have an uncertainty associated with that position. So how did we get there? We are certain, we're not certain. And then you conversely also have a measurement, which tells you that you are somewhere, right? A sensor giving you a measurement, and how much you trust that sensor is also encompassed into this standard deviation. And so this is why Kalman filters work so well as they do. So I'm going to make you even more confused because I'm now going to change notation, and this is by design. So Kalman filter notation is, I think, notoriously different to how it's like ultimately used. So even though it uses Gaussian distributions, and even though it uses kind of this Bayesian understanding of how you can utilize Gaussian distributions, they came up 70 years ago. I think they came up with their own notation, and they actually come up with the state obviously as being x. So this is no surprise, but the variance or the covariance matrix, as we're going to see in a second once we go into multivariate cases, defined with the p. So now we have a state x. We have some form of rate of change of the state somehow. This is the process model, so this is dx. And we also have an uncertainty related to that x, which is p. So this is the standard deviation of variance, the comparable. And we have the q, which encompasses the measurement uncertainty as well. So you can kind of assume this Gaussians again, and from prediction here, you can go into the update step that we have seen from the Bayesian filters, and you can define it quite simply as the rate of whatever state we have predicted as a prior here. You can feed it into an equation actually just taking into account the measurement, the relative measurement that we have seen at the next time step. So if that at the next time step we have seen the measurement z, for example, you would calculate whatever position we assume we are from the prior. We can also then calculate the position minus the actual measurement from the sensor as multiplied by the Kalman gain. And the Kalman gain is like the ultimate, the thing that is kind of the crux of the Kalman algorithm, mainly because if you want like an intuitive understanding of it, you can consider this as a ratio between how certain we are about the update x and the measurement z. And again, you can derive it as a homework if you'd like.
I didn't understand from the previous slide. How can you subtract z and x? Are they possibly on different scale?
So we are going to go into scaling and
x is the actual position. Z is a measurement that can be done.
So I'm assuming here that the z is also a position. So we know where we are.
You don't get that.
You don't get that, and I'll tell you how to deal with it in a second. But yeah, so I'm assuming that z here itself is a position in some. So it's exactly the same form as the position here. Yeah, and you can define it basically the Kalman gain as a ratio between update and measurement. So if you will, so this is basically the ratio between the prior variance as given by the prior variance and the measurement uncertainty. So yeah, exactly. So how about the multivariate case? Analytically it is a little different, mainly because we now go into vectors and matrices. However, the underlying concept remains exactly the same, right? So it doesn't, like the whole idea of the filters doesn't change. So we predict and then we update, and we keep doing this kind of in sequence. Cool. So now we start to operate, as I mentioned, in vectors and matrices, as opposed to kind of singular value variables, and we can derive the multivariate case by kind of looking at the values. So I'm going to have a slide in a second that actually describes how the univariate case is similar to the multivariate case, but this is actually exactly what you mentioned, Andrzej, which is the idea that we don't exactly know if actually control isn't the best example, but we're going to see in a second with the measurements that because the measurement can be taken from a completely different form, we still need to transform whatever form that is into a state space, right? So this actually has been accounted for. But the idea again is the fact that you have some form of x, right? So you have the state or the state space, in this case a vector. You have an x which specifies, so this is your prior, so you have the position here. You have the f, which is the state transition matrix, and will outline the system as the system changes with time. Bear in mind, I also have an example for the multivariate case, so don't worry about it too much. so it's a state transition matrix, and it basically tells you how a system is going to change with time. So you define, you still need to define some form of a dynamic that the system is going to take as the time kind of progresses. And you can see the state of the state of the system at k-1. You have the computed prior. B and U, these are quite interesting and actually feed into the Bayesian filter notion of control inputs and actions. So this is this basically defines a control input. So this is the input to a system that you can kind of sense, or this is the, that you can provide. You can perturb the system with an action. In Kalman nomenclature, this means a control input, and this is mainly used for systems which use control, such as robots or planes. But you can also define a system not only as changing with time, but also how it kind of accounts for the perturbation from an action or some form of control. So you can still encode robotic control into a Kalman filter, which is quite neat. Obviously, P and P hat prior covariance and covariance at k-1. So covariance and state transition matrices. Covariance matrix defines covariance in a matrix form. So if you have for example, a two-dimensional vector space of state or position. So say we want to calculate a position and velocity, right? So you would have, actually I should have it, actually no, later, that's my example. So I'm not going to spoil it just now. But the idea is basically that you have a matrix which is, which defines the covariance and variance between variables. So if you have two-dimensional state space, you're going to have a 2x2 matrix, and that 2x2 matrix is going to define the variance or the covariance between the variables and the states themselves, as well as covariance of the states with itself. So, yeah, so confusion. Yes, so that's what covariance matrices do. The FPF transposed. This is an operation of matrices. It's called projecting the middle term onto the outside term. This is actually exactly it's a computation of kind of matrices multiplied into the measurement space. And Q stands for process noise. Process noise is like it's basically encoding the expected value of a white noise present in a process. Expected value in a very broad understanding, not quite expected value you can think of as an average, but there are some rules and limitations on that. So yeah. So as you said, this is a multivariate case of a prediction, and this scary thing is the multivariate case of an update. But as soon as you start looking at this, you start seeing that it's actually starting to slowly make sense. Because you can imagine that what's called the innovation covariance, or S, is going to update how uncertain you are about a specific measurement. You can then define H. Sorry, I shouldn't do that. You can define H. You can define the H as an actual measurement function. This will project the measurement space in order to perform the calculation. And this is mainly because there are readings and there are sensor readings which are not invertible, and this is the main reason why you would actually use this. And invertible sensor readings, you can think of, for example, if you have a sensor reading that is only giving you range, right, like a sonar, you can calculate the position. So you can't calculate the position from a range. Mainly because you can't kind of invert from where the range. So if you have a position somewhere on a 360-degree circle of what range could be, you can't really go back and see the position. So if you're not measuring things straight in your position space, then this is something to consider as well. R stands for measurement covariance. So however many different sensors you have, this however many sensors you or like this, however, this kind of encodes the uncertainty of a specific measurement into the space. So for example, if you have a sensor and that sensor has a a data sheet that says I'm uncertain, or like it has the specifications of a sensor given to you, you can encode that into a measurement covariance matrix, and yeah, it's going to recalculate and assume that a specific R is given to you, and that you are, whether you are more likely to trust your measurement, or whether you're more likely to trust your current position as you are. And K, we kind of covered. This is the optimal Kalman gain. So this is something we've talked about, which is the ratio between the measurement and the actual update. This is a term called residual. We don't really. This is like, you can think of this as a difference between the measurement and the prediction. So if we know the position themselves and we know the measurement, then we can project that measurement into a state space, and from the state space we can kind of calculate how uncertain we are, or this is basically the error term of how uncertain we are given some measurement. And the last thing that you can't see there is Z. So Z, obviously that's going to be, and I don't know how to get rid of that bar, but you can imagine a Z, and that's basically the vector space of your measurements. So if you have one sensor, doesn't work in the multivariate case, but if you have 3 sensors, then you would basically encode them into this vector space themselves. So you should basically because univariate case is just so much easier, at least for myself, to understand, I tried to make this correlation between kind of a multivariate and univariate case, and you can start seeing to see different, like the similarities between them, and you can see that when it comes to kind of prediction, you're basically doing the same thing, right? So if you have a state and you'd like to see how the state changes with time, this is exactly what is being encoded by the state transition matrix that we've defined before. So F. Also, this accounts for the fact that you have some form of control input. Unfortunately, the univariate, I didn't define that, but for P, the covariance matrix, again, is the same thing. So if basically you can, as long as you project that term onto the measurement, or like the state space, you can add the uncertainty you have with the specific kind of the white noise covariance. And again, this is the same thing happens with the similarities between updates. So if you have a univariate Kalman gain, this Kalman gain can be defined using number of different, but the innovation covariance can actually be used obviously to calculate the Kalman gain. The problem obviously is that there is a number of different operations that you need to take on matrices. The bigger the matrices, the harder it is to invert in good time, and so you might want to, when you're designing your Kalman filter, you might need to kind of keep that in mind. Same thing here. You can see the residuals, and you can see the updates for the updates for the states. Again, the Kalman filter is being used as a residual. The residual itself, I kept it as a one-liner, but you can basically see that we could have a variable called y, and that y would then be used to subtract the measurement from the state space, and the same thing for the covariance. Now, I obviously is the identity matrix, which is a matrix of diagonal ones. Yeah. Cool. So before I go into how to design this, let me just have a drink. But if there's any questions now, I'm happy to take. Hi.
Yeah, thank you. So the question I have is about nonlinear systems. Mm-hmm. You mentioned that you're not going to go through the extended Kalman filter or
no. So this is a very basic implementation of a Kalman filter, but you would go. Extended Kalman filter is the one that actually deals with nonlinearity, right? And so the idea there would be that you would perform what's called a system of local linearizations. So you would use something like actually very similar to what Errol mentioned, which is just Jacobian matrices, right, with the rate of change of a certain nonlinear system. So Well, I mean, obviously, this would be a lot harder to show you in like 1 hour, but...
No. The question I have is, well, for linear systems, as you mentioned, basically, you can argue that after some time, the estates you can represent the estates as in terms of Gauss as well. You have mean and you have uncertainty or deviation around it. So basically, you can, if it comes to any safety critical system, you can basically argue that with this amount of uncertainty, I am safe or I am unsafe because in the end, the estates are within this range.
Yep.
But when it comes to nonlinear systems and when you do, as you said, linearization around operating points and so on, then how could we have any argument like that to be able to say how uncertain I am or how certain I am in terms of what I have estimated?
So logically, if you were to estimate something in a kind of a nonlinear space, and you would have an understanding of like how the rate of change of something changes, right, with time, then technically you could encode that into what's called a process. Was it the measurement function? But the answer to this is I'm not entirely sure, but I think it would be basically encoded in one of the. Basically, you just add terms in order to account for that. So you would basically have. For example, you would have a term that actually defines the Jacobian matrix that you can do, and that Jacobian matrix would produce a residual, I think, in itself. So I think that's what I think, but that's a good question. And I'm going to take a note of this, and I'll send you an email. Yeah, any more? No. Yeah, so very basically the pipeline of designing a Kalman filter is fairly simple. Like you would define the state space, the state transition function f. You would then design a process, not noise matrix, and then you would design a control function, a measurement function, and a measurement noise matrix. And the example I want to do, hopefully if I have time, I can probably show you it in like a code-based implementation. So let's hope if I have actually, what is the time? How's the time looking? Am I over or under? How does it work?
You are early.
Early, okay. That's not too bad. We can give a break, yeah. Oh yeah, okay, yeah. So we can have a break, yeah. And then after break, I'm going to go through this. Hopefully, show you the code, and you'll see that it's like 3 lines of code in order to implement this. And then from then on, we can go on to the actual practical session, which I hope you guys have prepared and are all ready to go. And if not, then we can come up with some. Anyway, yeah. Yeah.